In the last lecture, we have seen how to analyze two single phase transformers connected in parallel. However, in that the last example, the transformers that were connected in parallel had same no load voltage. Now, we will examine what happens when the no load voltage of the parallel connected transformers slightly differ. It should be remembered that single phase transformer whose no load voltages are different can be connected in parallel. However, this difference should not be very large, otherwise a large circulating current will flow through the transformer even in no load. So, let us try to get a feel of this through an example. Let us say the first transformer. So, two transformers are connected in parallel. Two of these transformers are connected in parallel. Let us call it transformer 1 and this transformer 2. Both input and output are parallel. Let us say transformer 1, this is 600 kVA, the series impedance Z1 equal to 0.0198 ohm angle 79 degrees, and no load voltage is of this transformer is 445 volts. For the transformer 2, the kVA rating is 300 kVA. The series impedance Z2 is 0.0304 angle 73 degrees, and no load voltage equal to 455 volts. Let us, they are connected in parallel and supplying a load current of 1800 ampere at a lagging power factor angle of 0.8 pf lag. We have to find out the no load circulating current circulating current, that is when this load is not connected, what will be the current circulating through the transformers. Then the load voltage and load kVA, this is the load voltage VL, and the kVA supplied by individual transformers. So, that is the problem. Please note that here there is a small difference between the no load voltage of these two transformers. In order to solve this problem, let us draw the equivalent circuit referred to the load side. Incidentally, the impedances given are referred to the low voltage side of the transformer. So, the equivalent circuit will be E10 in series with Z1 supplying the load, this is the load current IL, E20 connected in parallel, this is Z1, this is Z2, E10 equal to 445 angle 0, E20 equal to 455 angle 0, since they are co-phasor, they are connected to the same supply. The current supplied by first transformer is I1, current supplied by second transformer is I2, and the phasor sum of I1 and I2 is IL, which is 1800 amperes at 0.8 power factor lag. This is the load voltage VL. Let us first find out the no load circulating current. In order to find that, we assume that the load branch is open, that is load is disconnected, then obviously the no load circulating current I0, magnitude of I0 equal to mod E10 minus E20 divided by Z1 plus Z2. Now, from the given data, Z1 plus Z2 is equal to 0.05 angle 75 degrees, and mod E10 minus E20 is equal to 10 volts. Therefore, mod I0 equal to 10 divided by 0.05 equal to 200 amperes, which is not small. So, first part of the problem is solved. In order to solve the next two parts, we will have to solve this circuit. To solve this circuit, we draw the Thevenin equivalent this circuit across the load branch. Thevenin equivalent circuit consists of a Thevenin source VTH and a Thevenin impedance ZTH. So, the Thevenin equivalent circuit will look like this. ZTH, how to find ZTH? First open the load, short the source and look from this terminal the equivalent impedance, which will be Z1 parallel Z2. Which is Z1 Z2 divided by Z1 plus Z2. This comes to 0.012 angle 77 degrees. How do I find out VTH? In order to find VTH, that is the open circuit voltage at this terminal, we will have to apply superposition theorem, that is assume one of these source at a time and find out the voltage here and then add them. While considering one source, the other source will be shorted. So, the contribution to the open circuit voltage due to this source will be Z2 divided by Z1 plus Z2 into E1 0, and contribution of this source will be Z1 divided by Z1 plus Z2 into this source. So, VTH should be equal to which can also be written as so VTH comes to 445 angle 0 degree plus 3.96 angle 4 degrees, which is approximately equal to 449 angle 0 degree, because the contribution of the perpendicular component due to this is very small. So, we have the values. Now, the first job is to find out the load voltage VL, which is across this terminal. How do I do that? In order to do that, let us draw the phasor diagram with VTH as the reference. This is VTH. Let us say the load current is at some angle IL. Now, the drop due to the load current will be IL into ZTH. So, it will be IL ZTH into angle of ZTH with respect to IL. So, this angle will be the angle of ZTH, which is theta TH equal to 77 degrees. We have got the angle of ZTH to be 77 degrees. So, let us say this is the magnitude IL ZTH minus IL ZTH. Therefore, the phasor VL will be this. This is VL. Let us say this angle is delta and the power factor angle phi is given as cos inverse 0.8. Therefore, the angle between VL and IL ZTH, this angle is same as this angle, and this is theta TH minus phi. So, this angle equal to theta TH minus phi, which is equal to 40 degrees. Hence, from this phasor diagram we can write this is VTH, this is VL. So, mod VTH sine of the angle delta, which is the perpendicular component of VTH on VL, this is equal to same as the perpendicular component of IL ZTH on VL. And the angle is 40 degree. From here we get sin delta equal to 0.0309 and cos delta equal to 0.999 and VL mod VL equal to mod VTH component of VTH minus component of ILZTH cos delta minus here we know IL mod IL equal to 1800 amperes. This is equal to 432.24 volts. What is the angle delta? Delta equal to cos inverse 0.999. Which comes to 1.77 degrees. So, VL vector equal to 432.24 volts angle minus 1.77 degrees if E10 and E20 are taken to be the reference phasors. Therefore, load kVA will be magnitude of the load kVA equal to mod VL mod IL by 1000. So, this comes to 778 kVA at 0.8 PF lag. So, that answers the second part of the question, what is the load voltage? Load voltage phasor is this, magnitude 432.24 volts, angle minus 1.77 degrees and load kVA is 778 kVA and 0.8 power factor lag. The last part of the question pertains to finding out the kVA supplied by individual transformer. For that we will need to find out the currents supplied by individual transformers. Now that we know the VL phasor, we need not refer to the Thevenin equivalent circuit anymore and we can come back to the original equivalent circuit of the two transformers. We will find out the currents I1 and I2 and then find out the kVA supplied by them. So, I1 vector will be E10 minus VL divided by Z1. This is equal to 445 angle 0 degree minus 432.24 angle minus 1.77 degrees divided by Z1 is equal to 0.0198 angle 79 degrees and I1 comes to 932.72 amperes angle minus 32.7 degrees. Similarly, we can find out I2, this is given by E20 minus VL divided by Z2 and after calculation this comes 868 amperes angle of minus 42.6 degrees. It should be appreciated that the currents I1 and I2 are not in phase. So, the transformer is not optimally utilized in this case. So, KVA supplied by transformer 1 this is equal to mod VL I1 divided by 1000 this comes to 403.16 kVA at a lag angle of I1 minus the lag angle of VL at a lag angle of 32.7 degrees minus 1.77 degrees, which gives a power factor of 0.858 lag. Similarly, we can find out the KVA supplied by the second transformer. This is comes to 375 kVA at a lag angle of at a 0.755 pf lagging. So, that is how we analyze parallel connected single phase transformer when their no load voltages are not equal. So far, in our analysis and treatment of single phase transformer, we have tactically assumed that the applied voltage, flux, currents are sine waves in steady state, and that is why the phasor analysis and steady state complex impedance based equivalent circuit analysis was applied to single phase transformer. But in a single phase transformer, the applied voltage, even if it is sinusoidal, the current drawn may not be sinusoidal, particularly at no load. This is due to the nonlinear nature of the magnetic core of a practical transformer, which exhibits saturation and hysteresis. So, we will see how these nonlinear properties of the magnetic core affect the performance of a single phase transformer. So, this is the single phase transformer. Let us say at no load, with the rated applied voltage V1 at open circuit. We will also assume that the resistance of the winding is negligible. Therefore, the applied voltage V is exactly balanced by the counter induced EMF E. But we know this is the mutual flux phi m we know V 1 equal to E equal to N 1 d phi m dt. Now, if V 1 equal to, let us say, V m sin omega t, we know phi m will be lagging V 1 and E 1 by 90 degrees, and it will be given by minus phi m cosine of omega t. The question is, what will be the no load current I m or magnetizing current I m if we assume this magnetic core to have nonlinear properties like hysteresis and saturation. Since this is a nonlinear circuit, we will approach it graphically. So, we draw the flux versus magnetization current characteristics of the core, which is nothing but the BH characteristics of the core, but to a different scale. So, this is phi m and this is I m. This is the characteristics, BH characteristics of the core, showing a prominent saturation phenomena. However, if we also consider the hysteresis, then this characteristics modifies to the following. So, while increasing the flux increases following this path, however, while decreasing it follows a different path like this. Let us say this is equal to this is the level of phi m max. So, let us try to draw what will be the current I m if this is the phi m max. This is the characteristic BH characteristics. For that, let us consider the time variation of phi m. This is the time scale. We have said that let us say this is the applied voltage, this is the applied voltage V 1, this is V1. The flux phi m will be lagging this by 90 degree. So, let us say this is the flux waveform. Phi m. In order to find the current waveform I m due that will generate this flux phi m, we take the help of this magnetization characteristics. Let us say at time t equal to 0, phi m is at its negative peak corresponding to this point in the magnetization characteristics. So, magnetization current is at its negative maximum. Let us say here. Now, as the flux becomes increases and becomes positive, goes from negative to positive, the flux follows this path of hysteresis. Hence, when the magnetization current is 0, there is still some negative flux in the core, although small, but there is some negative flux. So, at the 0 crossing of the magnetization current, there will be a small negative flux in the core. So, let us say this is the 0 crossing instant of magnetization current. Similarly, when the flux is 0, the magnetization current has a small positive component. And when the flux reaches its maximum value, magnetization current also reaches its maximum value. On the return, when the magnetization current is 0, there is a small positive flux equal to what was there in the negative flux when the magnetization current was 0 in the previous subcycle. So, let us say this is the negative going 0 crossing of the magnetization current, and when the flux is 0, magnetization current is already negative and it comes back to this point. So, the waveform of the magnetization current will look something like this, I m. There are a few things to note about this waveform. First, this is not sinusoidal. Although voltage and flux waveforms are sinusoidal, the magnetization current definitely is not sinusoidal. So, any non-sin, but it is periodic and has the same period as the voltage and the flux. Therefore, this magnetization current can be decomposed into its Fourier components, and if one does that exercise, it will be seen that the magnetization current has a fundamental frequency component, the whose frequency is same as that of the applied voltage. In addition to this fundamental frequency, it has all odd harmonics of the fundamental, that is the third harmonic, fifth harmonic, seventh harmonic, etc., of which third harmonic is the most prominent. The second point to note is that the zero crossing of the magnetization current and flux do not coincide. The zero crossing of the magnetization current occurs before the zero crossing of the flux, that is, but the zero crossing of the flux occurs when the applied voltage is at its peak. In terms of phasor, the flux phasor lags the voltage phasor by 90 degree. However, as the magnetization current waveform leads the flux waveform, so the even the fundamental component of the magnetization current can be decomposed into two parts. One is in phase with the flux waveform, which lags the supply voltage by 90 degree. Another is a small component which leads the magnetization current and hence in phase with the applied voltage. This in phase component of the current supplies the losses due to the hysteresis. Of course, in a practical transformer, in addition to hysteresis loss, there will also be eddy current loss, but the current responsible for eddy current loss will be drawn from the supply, but it will be sinusoidal because the current induced due to flux variation in the core are sinusoidal. So, to compensate for that, sinusoidal current will be drawn. So, another small sinusoidal component in phase with the voltage will be drawn to supply the eddy current losses. So, these two components will constitute the total no load current I 0. At this point, it should be mentioned that in our treatment of the harmonics, we have considered the resistance of the primary winding or the winding to which voltage is applied to be negligible. However, if it is not so, then due to this nonlinear nature of the no load current, there will be nonlinear voltage drop across the resistance, and hence the even the back EMF or the counter induced EMF or the flux waveform will also not be sinusoidal as we have assumed here. But in a normal transformer, the assumption of negligible stator resistance, negligible winding resistance is usually valid. However, there is some precaution that needs to be taken. For example, suppose we want to perform no load test on a single phase transformer it is done on the LV side, but let us say the available supply voltage is larger than the rated voltage of the LV side, in which case we can reduce the applied voltage by connecting a resistance. A variable resistance. However, this is not recommended, since if we add additional resistance, then there will be non-sinusoidal current flowing under no load condition through this transformer, and which will make the applied voltage waveform also non-sinusoidal because of non-sinusoidal harmonic drop in the added resistance. So, this circuit is not recommended for doing no load test. If such a situation occurs, then the recommended practice should be to use a auto transformer or a variac to adjust the supply voltage to the required level. This will not distort the applied voltage with harmonics. This is the recommended practice. This should not be done. So far, we have been concerned with steady state operation of single phase transformer. However, before attaining steady state, when we just switch on a transformer, it goes through a transient. So, let us now look into what happens when a voltage is switched on a transformer. So, this is our single phase transformer. Let us say this is being switched on at t equal to 0, is switched on. Let us say the voltage, the transformer is on no load, at the voltage is V 1 equal to V m sin omega t plus phi. As before, we will assume that the resistance of the winding is negligible. So, once the transformer is switched on, the core flux is given by and since we have neglected the resistance, U 1 equal to V 1 equal to V m sin omega t plus phi. Solving this, we get phi m equal to plus a constant of integration E. Now, let us say before this switch was turned on, the phi m had a initial value of phi m 0, that is phi m at t equal to 0 equal to phi m 0. Now, phi m 0 need not be 0, because in a practical transformer we have seen due to hysteresis, even when the magnetization current is 0, the core flux may not be 0. This is called the residual magnetism, and there may be some residual magnetism in the core due to previous excitation. So, in general phi m 0 will not be 0. In that case, how do we find out phi m 0? By putting t equal to 0 in this equation. So, phi m 0 equal to minus V m by n 1 omega cos phi plus A. Therefore, A equal to phi m 0 plus V m by n 1 omega cos phi, and the complete expression of phi m is given by phi m equal to phi m 0 plus V m by n 1 omega cos phi minus cosine of omega t plus phi. Now, this will be the expression of phi m, and depending on the value of phi and phi m 0, its waveform will differ. For example, if both phi m 0 and phi are 0, then phi m becomes please note that at omega t equal to pi, the value of phi maximum value of phi m can be phi m max can be equal to 2 V m by n 1 omega. Usually this is the maximum value of phi m, that is phi m maximum can be twice its steady state peak value. The situation will be worse if phi equal to 0 and phi m 0 is greater than 0, in which case phi m will be phi m 0 plus V m by n 1 omega 1 minus cos omega t, and phi m max can be equal to phi m 0 plus 2 V m by n 1 omega. In this case, please note that at omega t equal to 0, value of phi m is 0. In fact, phi m never becomes negative in a cycle. So, the flux in this case is completely positive even in this case. However, we have the case where phi m 0 equal to 0 and phi equal to pi by 2, then phi m equal to cos pi by 2 is 0 minus cosine of omega t plus pi by 2. This is equal to V m by n 1 omega sin omega t, whereas V 1 in that case becomes V m sin of omega t plus pi by 2, which is equal to V m cosine omega t. Now, it should be noted that changing phi means changing the instant at which the switch is closed. Phi equal to 0 means we close the switch at the positive going 0 crossing of the voltage waveform. Phi equal to pi by 2 means we close the switch at the peak of the voltage waveform, and in those two cases we find that the transient expression of phi m are very different. In one case the phi m magnitude can be almost twice the steady state magnitude of the flux, while in the second case we find that the phi m magnitude will be just equal to the steady state peak magnitude of the flux. Now, what is the effect of this switching on the current drawn? For that, let us again consider the BH characteristics of the transformer. Please note that since this is phi m, in case where phi m is equal to 0 and phi is also 0, we see that the peak value of the flux, at least in the first cycle, can become almost twice the steady state peak value of the flux, which is almost double this value, but due to saturation the current drawn will not be double, current drawn will be very large. In fact, it is not unusual to have the currents almost 8 to 10 times the full load current of the transformer, which means it is about 100 times the normal magnetization current of the transformer. Therefore, in case you switch at this instant, the magnetization current of the transformer will be very large for the few initial cycles, and which will gradually decrease, because we have assumed the winding resistance to be 0, which will not be 0, but for first few cycles the current can be really very large and completely positive. Please note that in this expression phi m never becomes negative, hence I m also never becomes negative. This phenomenon is called the magnetic inrush in a single phase transformer, and the severity of the inrush will depend on the instant and at which the transformer is switched on. For example, at positive going 0 crossing, if we switch on the transformer, then the inrush current will be maximum, whereas if we switch it on at the positive maximum, there will be almost no inrush current. Methods have been developed to detect the voltage waveform and the switch transformers accordingly. Please note that the situation will be worse if there is some residual magnetism in the flux, because in that case the peak value can be even larger than twice the steady state peak. So, the single phase transformer protection device should withstand this magnetization current. Thank you.